Hi everyone. Sorry about the delay in getting this prepared. Today I'm going to be talking about a couple lectures worth of material, and we're going to try and go through this a little bit briskly. So feel free to pause anytime here and follow along. We'll also try to break this into a couple chunks, so this will appear as a few different videos, but this will all be part of the same makeup lecture. Just to give you an idea of some of the things that we'll be talking about in this video today, we're going to have, we're going to have 4 sections here. Okay, so the first of these is where we're just going to be talking about solutions of ionic compounds. Okay, and in this section, part of what we're going to be discussing is going to be, let me review here. So this is going to be partially talking about some of the differences between electrolytic solutions and non-electrolytic solutions. So what we mean here is that certain types of solutions, and as we'll see, these include things like sodium chloride, for instance, will break apart into ions that can act as charge carriers. But certain other types of solutions will not be able to conduct electricity because what they dissolve into is not ionized. Okay? An example of that one might be sugar. So sugar and salt will be our 2 examples here when we talk about this. So just to give us a bit of a preview there, one thing we might say is that an example of an electrolyte solution, and here I'm going to use that abbreviation SOLN. So an example of this might be aqueous sodium chloride. And the reason for this is that when we put sodium chloride into water, it's actually just going to fully split apart into 2 different types of ions. Okay, now for reasons of copyright, I can't show you some of the pictures that I'd like to show you from the book. So what I'm going to recommend is that you pull up the book in a new tab and just follow along with some of this. I'm going to try and call your attention as we go through here to a few different figures in your book. And if you follow along with these, they should give you a picture of what I'm talking about. So in this example, for instance, what I will say is that if you want, you can take a look at, in your book, figure 5.8, which will be on page 177. Okay, this will show you a picture of ionic sodium chloride, or the ionic compound sodium chloride, arranged into a lattice, which is to say an alternating series of positive and negative ions. Okay, and you'll see that water molecules are approaching this, and because we've already talked a little bit about how water molecules contain a partial negative charge and a partial positive charge, that might look like this. We've got an oxygen atom, and then we've got 2 hydrogen atoms over here. Okay, and we're going to say that each of these has a partial positive charge. And here we're using the lowercase Greek letter delta. Okay, this is just a convention for a partial charge. Okay, and then likewise, we can say that the water molecule has a partial negative charge. Well, we already know, right, that when sodium forms an ion, it's going to form Na+, Na1+ specifically. And we know that when chlorine forms an ion, specifically when it forms the chloride anion, it forms a Cl- charge. Okay, so one thing that we're going to talk about a little bit here is how there's interactions that can happen between the partial negative charge of the chloride the fully negative charge of the chloride and the partial positive charge of the hydrogens in the water molecules. So let me label these. These will each be hydrogen, and our friend over here will be oxygen. Okay, so right, there's going to be interactions between the partial negative charges in the water molecule and the sodium ions, and there's going to be interactions between the partial positive charges of the water molecule and the chloride anions. So what happens is that you have a lattice here that dissociates, it splits apart into just Na+ and Cl-. Right, our lattice might look something like this. And it would just stack like this in 3D space. And so I'll just complete a couple layers of this here. And as the water molecules approach this lattice, they can approach these variously positively and negatively charged atoms here, and they can actually steal them away from the lattice. Okay, so you would have several water molecules coming up and interacting with these cations and anions. Okay, so that's one of our examples here is an electrolyte solution. And because of the fact that these are positively and negatively charged, let me write this on here as well. These can actually conduct electricity. Okay, so that's why we call these electrolytes. The light part comes from the word of like electrolysis, right? The lysis part there means splitting apart. So here, as this compound splits apart, right, these ions here can conduct electricity. So we call this thing an electrolyte. Okay. Now, by contrast, we also have non-electrolyte solutions. And what these are is solutions that, it's not to say they won't dissolve, but rather non-electrolyte solutions, when they dissolve, do not form charged particles. So this is one I don't want to try to draw. Let me go over here to the browser, and I'll just use my mouse for this. So if I show you, for instance, a sucrose molecule here, when you dissolve sucrose, which is a type of sugar, when you dissolve this in water, it forms molecules like this, right? Well, it doesn't form molecules like this, rather, it breaks apart from a solid into individual molecules of this. Now, there may be many associations between water molecules and these individual molecules, and that's why the overall solid breaks apart. The water molecules still do interact with this molecule, and thus break it apart from the solid form. However, though, the thing I want to point out, though, is that in this case, this molecule as a whole is not charged. Okay, there are partial charges throughout this molecule, true, but they're not nearly as strongly charged as the sodium and the chloride anions, or the sodium cation and the chloride anion here. So in the case of sucrose, for instance, when sucrose dissolves, so we could say, well, honestly, it wouldn't even really make sense to draw a reaction for this one, because when it splits apart, it's just going to split into individual molecules. So what we're going to say in this case is that because the molecules that it splits apart into are not ionized, the solution that forms from a non-electrolyte is not going to conduct electricity. Okay, so let me just write this out here. Okay, and let me just clarify here. I'm going to say because these types of molecules, okay, because there certainly are molecules that bear charges, but in this case we're talking about specifically types of molecules that do not bear charges when they split apart. Another example of this, for instance, might be glucose, or it might be carbon dioxide. Right? In these cases, if you have, well, maybe I shouldn't use the example of carbon dioxide because it's not a solid that would dissolve in an aqueous solution. But different kinds of solids that would dissolve in aqueous solutions, we can classify them as electrolytes or non-electrolytes based on whether or not they conduct electricity. Okay? So, since we're already sort of in the swing of this lecture, let's just go ahead and finish up this topic. And at the end of this video, I'll include a note for the other 3 topics that we'll be talking about. Okay, so let me take a look here. We've already talked a little bit now about these 2 types of ionic solutions. And actually, I shouldn't say these 2 types of ionic solutions because let me be very clear about this. These kinds of solutions form from ionic compounds. Electrolyte solutions form from ionic compounds because when they split apart into ions. Non-electrolyte solutions, on the other hand, form from non-ionic compounds. Okay, we might even just say in this case, molecular compounds. Meaning that when these solids dissociate when they split apart in solution, they don't split apart into individual ions. They split apart into entire molecules that don't bear a charge. Okay. So again, our examples here will be, think of dissolving salt in water for an ionic compound. So I'll say, in this case, table salt, so that we think about sodium chloride. Okay, and then our example for a non-electrolyte solution here would be sugar. Okay, because when we dissolve sugar in water, it's not going to split apart into ionized species. It's just going to split apart into entire sugar molecules, each of which has the same formula as that species of sugar in general. Okay, as opposed to, for sodium chloride, when this splits apart, each of the species that it splits apart into is not the same chemical formula as sodium chloride itself. Solid sodium chloride, for instance, is NaCl, but in aqueous form it splits into Na plus and Cl minus. Solid glucose is C6H12O6, and when it dissolves in solution, it's still C6H12O6. Okay, so this will be an example of sugar dissociated in water. And we'll say e.g. glucose or sucrose. Okay. Now, this covers the basic ideas of electrolyte solutions versus non-electrolyte solutions. So let's add a little bit of context to the idea of electrolyte solutions. So here what we're going to do, let's switch over to a new color here. Let's make this one blue. We're going to say that electrolyte solutions can be further classified into two types. One of these types is what we're going to call a strong electrolyte. Okay, a strong electrolyte, like for instance sodium chloride, is going to completely split apart into its constituent ions. Okay, so as an example here, when we have an example of sodium chloride, this will split apart into sodium plus and Cl minus. Okay, but we're going to use a complete forward arrow here. In fact, I'll say a single forward arrow, because what we're saying here is that this is essentially a one-directional reaction. Okay, so we're going to say one-directional reaction. I'm sure my youngest sister would love that phrasing. Absolutely obsessed with one direction. She's going to be so embarrassed that I said that in here. I don't care though. Okay. Other example here, weak electrolytes. So in these cases, these are species that split apart in solution, just not completely. Okay, so let me see, what is a good example that your book shows for that one? Well, in this case, it actually shows an example of an acid, and we'll talk in just a second here about how these concepts of strong and weak can be applied to acids as well. So let me give you one more example here. Before we go back to our weak example, we'll say another example here will be hydrochloric acid. Okay, so this is one that we've now worked with in lab. We know that when hydrochloric acid, or when HCl, is put into water, it completely ionizes. Okay, and I have a point I want to make about that idea here in a sec. But let me just finish what we're talking about here first. Okay. What we say is that for a strong acid, like hydrochloric acid, that this is going to completely dissolve in solution, basically 100%. Right? Every time an HCl forms, like by an H plus and a Cl minus colliding, for instance, it's just going to redissolve again. Okay, and what's really happening there is that there's such strong interactions between the Cl minus in the water and the H plus in the water that it's just going to be more convenient for this thing to split apart. When I say more convenient, I really mean energetically speaking. The whole thing is able to lower its energy by splitting apart. But we'll talk all about energetics of reactions later in the semester, so I don't want us to worry about that too much right now. So here's an example of a strong acid, what we're going to say is this is near 100% dissociation. Dissociation, there we go. And by this word, just so we're clear, what I mean is splitting apart. Ooh, starting to write at a bit of a slant there. Let's get that fixed here. Ooh, that's hard to read. It's not even that much better, is it? Okay. So that's what we mean by this term dissociation. Now, how about a weak acid or a weak electrolyte? Well, here, one example that we can use is acetic acid. We saw this on our first exam, actually. We saw this as an example of a compound that is found in vinegar that actually gives it that vinegary property. So acetic acid here, which is not the same thing as vinegar, right? But it is an active component in vinegar that gives it the properties we recognize. So, let's get rid of that. So what we would say is that for a weak acid like acetic acid, or a weak electrolyte like acetic acid, before I do that, let's put our phase here. When we put this species in water, when we make this an aqueous solution, what happens is that it will split apart, just not 100%. And in fact, for many weak acids, nowhere near 100%. It's actually quite a small fraction. But we will have a section just a little bit ahead of this where we talk some more about, actually in the next section, we'll talk a little bit more about acids. So for now, before we talk too much about that, I just want to emphasize that in this case, what we mean when we say that this is a weak electrolyte or a weak acid is we're going to use a bidirectional arrow. And the reason for this is that this reaction can happen in the forward direction, but it can also happen in the backwards direction. Let's say reaction happens both forwards and backwards. And the other thing I want to say about this is, let's see, both reactants and products exist in appreciable amount. Okay, so that's going to be different from the case of a strong electrolyte or a strong acid. And we'll come back to that point here in just a sec. Let me just write this out. So what I mean by saying that both the reactants and products are present in appreciable amounts is consider the case of hydrochloric acid up here. We said before that this is essentially a one-way reaction. Every time a hydrochloric acid is present in water, it's basically just going to split apart into H plus and CO minus. Okay? What that means is that the HCl here as a unit doesn't really exist in large quantities in water. It's just going to split apart. Okay? So we're going to have the products present in very large amount with the case of hydrochloric acid, but we're not going to have much of the reactant. So that's what we mean down here when we say that both reactants and products are present in appreciable amounts. We mean that both the non-dissociated form, okay, the non-ionized form, so acetic acid, is present in an appreciable amount in the solution, but also we have lots of H plus and acetate ions. Whereas for the case of hydrochloric acid, we have lots of H plus and chloride anions, but very little of the actual hydrochloric acid undissociated species. Okay, so let's see. One more point I want to make about these weak acids is that really, I say that both of these are present in appreciable amounts, both the reactants and the products, but the truth is most of the weak acid, or a weak electrolyte in general, does not dissociate. So in fact, only a little bit of it dissociates, whereas in the case of hydrochloric acid, we mostly have product, right? We mostly have H plus ions and chloride anions, but not much of the undissociated species. In a weak acid solution, actually most of what we have is the undissociated species. we actually don't have much of the product. And that's the characteristic difference between a strong and weak acid. So let me go ahead and give you a few examples of these. I think this will be one of the questions I will have you answer for your quiz. Okay, let me find where this table is, and then I will tell you where it is. Okay, although this is getting a little bit ahead of this, we'll talk more about this in another section, I just want to go ahead and draw your attention to page 189 in your textbook. This will be table 5.2. This contains a list of strong acids and bases, and it also here contains a few common weak acids and bases. The first question for your quiz will be, what are the strong acids and strong bases that I want you to memorize? Okay, and I'm going to have you write these out for yourself just to get in the habit of thinking about these. But the truth is, we're going to have really just 6 strong acids to memorize. As far as strong bases go, I'll give you some examples, but they all share one species, which is hydroxide, so it should make your life a little bit easier. Here are the strong acids I want you to memorize. Okay? I want you to be able to recognize these species, and I want you to be able to create their chemical formula if I give you the name. So we're going to say, here is our list of strong acids. First on here will be hydrochloric. So hydrochloric acid is just going to have the formula HCl. This is one we should hopefully know how to form. And in fact, looking at this, all of these but one are a polyatomic ion we've already had on our list to memorize, so we'll also gain a new one to memorize here. But that'll be at the very end of our list. Okay, next, hydrobromic. And these first 3 that you see on here, you'll notice that these are all acids formed from halogens, which is group 7 on your periodic table, or the one all the way on the right, except like one to the left of the noble gases. So that includes elements like fluorine, chlorine, bromine, etc. You'll notice hydrofluoric acid is not on this list. Okay, and we'll talk a little bit, oh, there I go, starting to write it. Hydroiodic is what I meant, right? We'll talk in a minute about hydrofluoric acid, but I just wanted to call your attention to that because although these first 3 are all halogen-based acids, halogens are the names of the elements like fluorine, chlorine, bromine, etc. Despite the fact, hydrofluoric acid is actually a weak acid. Okay, what's happening in that case is that fluorine likes its hydrogen so much that it actually doesn't split apart that much unless you give it a really good reason to. Okay, but we're going to get to the reason for something like that much later in this course with a concept called electronegativity. So the next one I'm going to want us to memorize as being a strong acid. And that's what I mean by memorizing these. I want you to know that these are all strong acids that will pretty much completely dissociate in solution. All right, we're going to treat these 6 acids as completely splitting apart. So nitric acid, that's going to be another one here. We know by this point that this is composed of the nitrate anion. Tried to write A for anion. Okay, so that's what that one is composed of. Next, another one that we hopefully recognize, sulfuric. Okay, so this one comes from the sulfate anion. So this will be H2SO4. And it comes from SO4, 2 minus, hence the 2 hydrogens there. Which we're going to call this ion sulfate. Okay, and then finally, this one involves a polyatomic ion that we didn't actually commit to memory before, but we will now. And the nice news is that it's pretty similar to one, what am I doing? What I want to write is perchloric acid. The nice news is that the formula for this one is actually quite similar to chloric acid. Right, we know chloric acid, we know chlorate, so we'll put that over here. ClO3 minus is going to be chlorate. We also know ClO2 minus is going to be chlorite. Well, there's actually two more in this family. There's ClO minus, which is called hypochlorite. Hypo here meaning low. At least I think it means something like low or under or something like that. And the reason here is that it has an even lower amount of oxygen here. But on the other side of the spectrum, we have perchlorate. Okay, and that's the name of this polyatomic ion here. So, when we come over here to perchloric acid, hopefully by now we recognize that the ic acid part comes because it's perchlorate. Okay, so perchlorate here is going to be HClO4. Sorry, this kind of looks like a 5. Ooh, that's so much worse. There we go. A little better. Okay, so this is going to be the 6 strong acids I want us to memorize. I'm going to give you a couple examples of strong bases, but I hope that you'll see that these are a little bit easier to remember because they all will involve hydroxide. And in this case, there's only going to be 5 I'm going to show us. The first of these will be sodium hydroxide. And you'll see very quickly, all of these will be some form of metal hydroxide. So this one is NaOH. Remember that OH minus equals hydroxide. So that's one polyatomic we want to have memorized as soon as we can. Lithium hydroxide will be our next one. And as I'm going along with this, I hope that when I say the names of these, you're able to start thinking about how we would form the formula for that. So for instance, lithium hydroxide, we know lithium forms a +1 charge because it loses 1 electron. So this is going to form LiOH. Okay, 3 more for us. Next will be potassium hydroxide. And if I'm writing this as if you said to yourself, maybe that's KOH, well, hey, you're exactly right. Okay, calcium hydroxide will be our next one. I meant to write that over there. So let's grab this. I'll steal part of the P in the process, unfortunately. Okay. Now, as I write these names out, I want you to think to yourself, why do I not need Roman numerals on these? Right? Why would this not be calcium 2 hydroxide? Well, hopefully at this point, we might start to think, well, that might be because calcium is always going to form a +2 charge, and we really only need those Roman numerals in cases where the charge state of the metal will be ambiguous. So for instance, for iron, it probably would be ambiguous. But in the case of calcium hydroxide, well, we know that Ca will always form a 2+. So that one's going to be no big deal for us. And the last one here will be barium hydroxide. Now, I don't really want us to have to commit these to memory. The truth is they're all hydroxides, and most of these should be predictable to us based on the rules that are present in table 5.1. So let me write that over here. And we'll talk more about table 5.1 in the next video. Table 5.1 is the solubility rules. But the truth is, all 5 of these should be predictable based on the solubility rules table, which you will have on exams. I do want you to commit these 6 strong acids to memory, and likewise, I want you to commit to memory these 2 polyatomic ions. So perchlorate and hypochlorite, 2 that we did not commit to memory during the first bit. Okay, so now that I've said this, let's take a pause and look at what we have here. We have a small table here of some strong acids and strong bases. In other words, species that will always split apart into their ions when we put them in water. I want to emphasize, though, if it's not on this list, it's going to be, for our purposes in class, a weak acid or a weak base. So for instance, if I were to ask you, is hydrofluoric acid, HF, is that a strong or a weak acid? Okay, I want you to take a second to think about that. Feel free to pause here. I'm going to go ahead and answer that in a sec. Okay, so hydrofluoric acid. Well, we don't see it on our table of strong acids here, so that one's just going to be a weak acid. Another example here, acetic acid. Okay, I want you to pause for a second and think to yourself, acetic acid, we spell that this way here. I'll erase this in a second so that it's not just randomly here. But I want you to consider this acid here. How would we write the formula for this? Does this contain a polyatomic ion? Feel free to consult your list of all of the polyatomic ions. That is, I'll find that in a second here. I will want you to go ahead and take a look at that and identify, is this one of the polyatomic ions in our table? So that is on page 104. Let me write that here. Table 3.4 on page 104. I want you to take a look at that table and see if you can identify what polyatomic ion acetic acid is composed of. Okay, and then I want you to decide, is this going to be a strong or a weak acid? Okay, so if you look at the table on page 104, hopefully you see that acetate has the formula C2H3O2 minus. Okay, so this thing is what is called acetate. Acetic acid then would be HC2H3O2. Okay. Now H3O2, or I'm sorry, HC2H3O2, acetic acid. Is this a strong or a weak acid? Well, I don't see it in our table. So what I'm going to say is this is probably going to be a weak acid. And indeed, if we were to look at the table 5.2 on page 189, the one that lists the acids and bases, we would see in that case that this is indeed a weak acid. Okay, so let me take this. I'm going to move this down for us so that we can keep it, because I also want us to note that the acetate ions. Let me write that over here as well. I want us to memorize this one as well. Now we'll summarize all of this at the end, all of the new polyatomic ions I want us to memorize. But for now, I'm just going to go ahead and add that to our list, along with perchlorate and hypochlorite above. Now let me just take a look and see if there's anything else I want to talk about in here. Yeah, I mean, the next topic we'll talk about is acid-base reactions, something we've already discussed in class a little bit. So let me go ahead and summarize this video by giving you a preview of what the next sections of the video will be. We will go way up here and say, I'm going to take this arrow, bring us down a little bit. Where is my mouse? Okay. Well, that arrow could have looked better. Okay, video part 2 will be talking about acid-base reactions, as well as the so-called Arrhenius definition of acids and bases. This is named after the Swedish chemist, something Arrhenius. Let's see, is that in here? It's probably in here somewhere. You know, maybe not the most essential thing to what we're talking about here, but it's always nice to recognize the people who have brought us to where we are. I wonder if I'm going to see that somewhere in here quickly. Well, we'll talk about it in the next one if I find it. Okay, but so we're going to talk here about the Arrhenius definition of acids and bases. In section 3, we're going to talk about precipitation reactions. Another thing we've already talked about a bit in class, but I will go through it one more time so that we're all on the same page here. This part will also talk in more detail about the solubility rules. So some of you, most of you probably would have heard this in class already, but you will not need to memorize these. Some universities ask students to memorize the solubility rules, but you'll see for yourself, it's kind of an ugly table. And I think the best way for us to learn those rules well is to just work with them, as opposed to trying to commit them to memory before we really get the chance to build context for that. So you will not need to memorize these. A table of these will be provided on the exam. Okay, and finally, the last bit of this lecture, which is also completely new stuff, we'll be talking about gas evolution reactions. So these are cases where when you mix two species, a gas will form. Okay, sometimes you'll see that form in the form of bubbles. And so we'll talk about a few examples of acid-base reactions that also produce a gas. So let's say this is reactions that give off some form of gas. Okay, well that's going to bring us to the end of this video. I think what I'll do is give you one quiz question per video. Okay, and feel free to chat with each other about these. They are open notes, so I don't really mind. The first of your questions, though, where did I write that in here? Oh, the first of your quiz questions will be, I just want you to go through and write out for me all of the strong acids, and let's say the strong bases as well, that I want you to memorize. So let's go over and make a little bit of space over here, and we'll say quiz question 1. What are the strong acids and bases I want you to memorize? And we'll come back to this list as I make the other videos to add the other 3 questions here. All right.